Hello everyone, we are gathered to record Unit 3 of the course Automata and Formal Languages, Part 1. Today we will talk about regular operations, deterministic and non-deterministic finite automaton. We are still using the Sipser book and we are still in chapter 1 of the book. I would like to remind you the definition of regular language. A regular language is a language for which we have a finite automaton that recognizes it. It means that for each word of the language, we have a pass at the automaton that ends at accepting state. Let's see some examples. For example, for every symbol A in sigma, the language LA that is only one letter A is a regular language. We will show it later. For every word W that is built from A1, A2 till A end over sigma, the language is W, LW equals W is a regular language. The second example we will do later during the practice exercises. Okay, let's solve the first question. For each letter A in sigma, the language LA is regular. I advise you to stop the lecture recording and to try to solve this problem by yourself. I will continue with the example. So to prove that the language is regular, I need to build a finite automaton that accepts the language. I will use deterministic finite automaton, and to accept only one single letter A of the alphabet, I will use three states automaton. So let's see. I will start at Q0 state, and with letter A, I will move to Q1 and accepting state. From Q0 for the rest of the input letters of the alphabet, and you can write it large sigma minus A. I will move to the state Q2, which is a trap state. I cannot go out from the state. If we manage to finish if we get to Q2, there is no way to get out of the Q2. In Q1, after reading the single letter A, for the rest of the letters, we continue to Q2. So basically, here we have a deterministic finite automaton that accepts LA. During our course, we will compare our learning model with modern computer. So let's talk about finite automaton or finite state machine and the real computer. Both have CPU, central processing unit, of the fixed finite capacity. In automaton, our CPU is actually our states. We can do some memory or we can remember things with the states. In finite automaton, we don't have any input at all. Finite automaton is basically not a computational device, but a language recognition device. Finite automaton is actually a very restricted model of the modern computer with no memory apart from fixed central processor or fixed memory that we have. A finite automaton is called deterministic if for each letter sigma in sigma and each state q in q, there exists one unique transition. Delta qj sigma equals qk. So basically, if we look at the example here, we have the state qj and transition with the letter sigma to qk. What can be else? Please look at the two drawings below. The first drawing, for qj and sigma, we don't have any transition at all. And the second example, qj and the letter sigma, we have two transitions. We can move to qk and qi. So both cases are not deterministic automaton. we will talk about non-deterministic finite automaton later today. We have a set of regular operations. Union is a regular operation. If we perform union of two regular languages, the result is a regular language. Intersection is a regular operation. Complement is a regular operation. Minus is a regular operation. Concatenation is a regular operation, and we will prove and show it now. Union of two regular languages is a regular operation. The theorem is if L1 and L2 are regular languages, then so is L1 union L2. Or, in simple words, the family of regular languages is closed under union operation. How we will prove this theorem? Basically, we will prove it by construction. Since L1 is a regular language, we have some automaton, let's call it A, that accepts L1. Since L2 is a regular language, we have some automaton, let's call it B, that accepts L2. We want to build an automaton that accepts L1 union L2. So basically, we want to build some deterministic finite automaton, M, that will simultaneously move in two languages. Let's see two languages. L1 is the language of all W, W ends with 0. L2 is the language of all words of odd length. So here we have an automaton A representing or accepting the language L1 and automaton B accepting the language L2. So, how do we decide that some word belongs to our language? So basically we can run an automaton M for both languages. And we run W on automaton A. And if A accepts W, then M should accept W. Or we can run W on B, and if B accepts W, then M also accepts W. However, we have a problem. If I read W letter after letter, and let's say that I started with automaton A, and W was not accepted by A, I read all the letters, and there is no rewinding. I can't go back. So basically, I finished reading all the letters, and now I don't know what to do, because the word W did not belong to automaton A. I can't go back and start checking with B. So basically, I want some kind of simulation that I can do both moves in automaton A and in automaton B together. So basically, I would like to simulate A and B simultaneously. So to move simultaneously in two automatons, in two automata, I need a transition function from the state that actually is a double state, that we have a state from QA and we have a state from QB. So actually, I would like to talk about two tuple, QA, QB, where the first state is from the first automaton and the second state, QB, is from the second automaton. So let's see how it works. We have a word 11011. And now we would like to give this word 11011 to both automaton, and we would like to check if the word belongs to the language of the automaton. Okay, the first step, we move from P0 with 1 to P0 in automaton A, and we move with 1 from Q0 to Q1 in automaton B. The next input is 1, once again. We stay at the same state in automaton A, and we move from Q1 to Q0 in automaton B. Now we have an input letter 0. We move from P0 to P1 and from Q0 to Q1. In automaton A with 1, we move to P0. In the second automaton B, we move also from Q1 to Q0, and we have a last input letter. So, for last one, at automaton A, we stay at P0, non-accepting state, and at the second automaton, we move to the accepting state Q1. Since one of the states at one automaton is an accepting state, we say that the word belongs to the union language. So we know that the word 11011 belongs to the union between the language L1 and L2. So let's continue with the idea, how do we build the union automaton? If we have automaton A that recognizes L1 and it's given by its 5 tuple QA sigma delta A QSA FA, and we have automaton B that recognizes L2 and it is given by its 5 tuple QB sigma delta B QSB FB, we would like to construct a new automaton M. Once again, we would like to define a 5 tuple Q sigma delta QSF that recognizes L1 union L2. The basic idea that we explained before is to build a Cartesian product automaton M that in parallel runs on a string W in automaton B and in automaton A. So basically automaton M starts running from the initial state of both automatons, A and B, and continues for each input letter to move in two machines, in A and in B. So basically, our new states at the automaton B and at the automaton N will be the product automaton, the Cartesian product of QA and QB. Additional question. When we decide that the word W belongs to the language L1 union L2, we know that in union, it doesn't matter if the word belongs to L1 or to L2, it is enough for us. So basically, when we finish reading the word at the state R1 or R2, we decide if W belongs to our union language. If W belongs to L1, that means R1 is the final state. Or W belongs to L2, and the meaning is R2 is the final state. So basically, if we finished reading our word in both machines, and one of the states for automaton A or for automaton B is an accepting state, then we know that the word belongs to the union. So let's continue with formal definition of the union. So we will build a Q set of all tuples of the states RA, RB, where the first state RA is from automaton A and the second state RB is from automaton B. Sigma usually is the same sigma for the language L1 and L2. So it's the same sigma for both automaton A and automaton B. If we have different sigma, it's not a problem. We can define the union of sigma A and sigma B to be our new sigma for automaton M. Now we have to define a transition function. Basically, the transition function, we start from the couple RA, RB, and we continue to new state, which is once again a couple of states. So the transition is defined by transition delta A in automaton A when we move from the state RA and letter sigma, and transition to the second state RB is defined in automaton B by function delta B when we move from state RB and the letter sigma. So once again, as a result of the transition, we have two states, one from the automaton A and the second one from the automaton B. Okay, the starting state. We define QS to be a couple, QSA, QSB, where QSA is the starting state of the automaton A and QSB is the starting state of the automaton B. And finally, the finite set. First of all, finite set can be an empty set, but accepting state, the set F, is defined by, once again, couple of states, RA, RB. And for us, it is enough, or RA is, belongs to FA, is an accepting state of the automaton A, or RB is an accepting state of the automaton B, FB. Alternatively, we can write this definition F equals FA Cartesian product QB union QA Cartesian product FB. So it doesn't matter where we have a finite state, in A or in B. Okay, so let's go back to our example. We have two languages, L1 and L2. L1, the language is L1 has all the words or accepts all the words that of the odd length, and it is automaton B in our case. The language L2, the language of all words ending with 0, and in this example, it is an automaton A. We would like to define an automaton of the union or automaton for the union of L1 and L2. Basically, we would do this example in class. So I would like you to stop the lecture recording and try to draw the automaton according to the definitions that I gave before. Okay, first of all, we will start with the set Q of all the two tuples of our automaton. So basically, we will have the state P0, Q0, and it will be the starting state. We will have the state P0, Q1, and the state will be an accepting state since Q1 is an accepting state. We will have a couple P1, Q0, and here, once again, we are talking about accepting state, and additional state P1, Q1 is also an accepting state. Here we have both states. P1 is accepting in A, Q1 is accepting in B. So now let's define our deterministic finite automaton. So for each state, which is currently a couple of states, a tuple of states, we will have to define what we do for input letter 0 and what do we do for input letter 1. So P0, Q0 on 0 will move us to P1, Q1. Since we'll have transition from P0 to P1 in automaton A and transition from Q0 to Q1 in automaton B. P0, Q0 on 1 will transfer us to the new state P0, Q1. Since on 1 at the first automaton we stay at P0 and at the second automaton we move to Q1. Okay, now we continue. Let's continue from P0, Q1 state. Once again, we have to define two transitions. What do we do for 0 and what do we do for 1? P0, Q1, for 0, we move to P1, Q0 because that's what we are doing in both automatons. P0, Q1 on 1, we stay at P0 and at the automaton A, and we move to Q0 at the automaton B. Okay, the next state, let's choose P1, Q0. Once again, I have to define two transitions. What do I do with 0 and what do I do with 1? With 0, we move to the state P1, Q1, Why? Because we have a self loop at P1 in automaton A, and we move from Q0 to Q1 in automaton B. For 1, we return to the state P0 Q1, since we move from P1 with 0 to P0, and we move from Q0 to Q1 on 1. Okay, the final state that we need to complete is P1 Q1. Once again, P1 Q1 on 0 return us to P1 Q0. P1 Q0, P1 Q1 on 1 return us to P0 Q0. So here we have an example of the union automaton for the language L1 union L2. Okay, now we have to prove that the machine, the automaton M that we built, actually accepts the language L1 union L2. And once again, to prove the equality of the sets, we will prove equality of one side, or we will do bidirectional. Once again, we are required to give the formal proof that the machine M that we built actually accepts the language L1 union L2. And we will prove this equality by bidirectional inclusion. We will start with the word W belonging to L1 union L2, and we will prove that it is included to LM. And then we will do the second direction. We will start with the word W belonging to the language of machine M, and we will prove the inclusion in L1 union L2. So let's start the formal definition. We will take a word W that belongs to L1 union L2. We know by the definition of union that W belongs to L1 or W belongs to L2. That means that if we will start reading the word W in automaton A from the beginning state QSA, we will finish reading it in R1, the finite state, or that means that if we will start reading the word W in the automaton B from the beginning state QSB, we will finish reading it at the state R2, which will be an accepting state. So one of these two cases should be. So delta cap QSA QSB on W. Now I'm talking about automaton M that we built, where we have two tuple of the states QSA QSB on W. So according to the definition of delta function, we are talking about delta cap A QSA W, delta cap B QSB W. So we in parallel move on the word W in automaton A and in automaton B, and we finish reading at the state R1, R2, where we know that OR1 is an accepting state, FA Cartesian product QB, or R2 is an accepting state, QA Cartesian product FB. By definition of F in our new automaton M, delta cap from the state QSA QSB on the word W equals R1 R2 belongs to FA Cartesian product QB union QA Cartesian product FB. But by definition of F, this union is resulting to F. So we have a couple of states, R1, R2, that belong to F. Therefore, the word W that we started with belongs to the language LM of the machine of the automaton M that we just finished building. The second direction, we are doing more or less the same. We start with the word W belonging to the language LM, and we define what does it mean that the word belongs to the language LM. That means that if we start reading it from the initial state, QSA, QSB, on word W, we will finish reading it at the finite state of the automaton M. And that means that delta cap function in automaton A, when we start reading from the state QSA the word W, or delta cap B, when we start reading the word W from the state QSB, it ends at the finite state. By definition of the finite state of the automaton M, we know that or we have delta cap A, QSA W belonging to FA, finite state of the automaton A, or we have delta cap B, QSB W belonging to FB, belonging to the some finite state in automaton B. Therefore, according to what we have a word W or belonging to L1 or belonging to L2. By definition of union, we have a word W that belongs to L1 union L2 that actually, when we now finished the second direction of inclusion, so therefore we know that LM actually equals to L1 union L2. Okay, the next operation is intersection. Basically, the definition is the set of regular languages is closed under intersection operation. What is the meaning of closure? If we have L1 and then 2 regular languages, therefore L1 intersection L2 is also a regular language. Once again, how we will do it? What do we want to do? Once again, we want to build an automaton that moves in parallel in automaton A of the language L1 and in automaton B of the language L2. And now we know that the word belongs to L1 intersection L2 only if both automatons A and B finished reading W in the accepting state. So now when we define a set F of the finite state of the new machine M, we will need that both states that we have in automaton A and in automaton B will be an accepting states. Once again, we will take the word L1 and L2 from previous example, the words of odd length and the words ending with 1, and we will define L1 intersection L2. We will do it during our practical exercises when we will have our Zoom meeting. The formal definition of intersection automaton will be actually relatively the same as the union. We will start with automaton A that recognizes language L1 and will have its 5 tuple. We will take automaton B that recognizes L2 with its 5 tuple, and we will construct a new machine, new automaton M, that actually recognizes the intersection between L1 and L2. How do we build a set of states in this new automaton? Q will be the set of all couples, all Cartesian products of QA Cartesian product QB. So once again, we will have a couple of states. The first state from automaton A and the second state from automaton B. Once again, sigma will be the same for A and B if we have the same alphabet. If we have different alphabet, we still continue with union between alphabet of automaton A and alphabet of automaton B. Transition function will be the same. We will start from state, which is actually a couple of states, RA, RB, and we will have some input letter sigma, and we will have to decide where do we move from RA, RB on sigma. To decide where do we move, we will check where do we move in automaton A, delta A, RA sigma, and we will check where do we move in automaton B, delta B, RB sigma, And then we will have a couple of states, which is actually our transition. Okay. Later, we have to define an initial state, starting state. QS will be a state where we have the initial state of the automaton A, QSA, and the initial state of automaton B, QSB. And our final state, here we have a difference between union. Now our finite state or our set of finite states will be a set of all couples RA, RB, where RA belongs to finite states of automaton A and RB belongs to the finite states of automaton B. Or we can define it in alternative way, F equals FA Cartesian product FB. So now to accept the word, we need that automaton A finish reading it in accepting state, and also automaton B finishes reading it in accepting state. To prove that the language LM equals to L1 intersection L2, we do the same proof as we did before, just change the definition of union to intersection. The class of regular languages is closed under complement operation. That means if we have L regular language, then L complement is also a regular language. How do we prove it? If you remember, during our practice session last week, we solved the same problem. We built an automaton that accepts all words that have substring 110, and later we built an automaton that does not accept all the words having substring 110. So basically we know how to build a complement automaton. So it will be the same automaton. So we have automaton L that accepts L. We will use the same automaton. What we will do, we will just change accepting states to rejecting states and rejecting states to accepting states. Because in automaton A, we would like to accept the word if, in new automaton M, we would like to accept the word if it was rejected by automaton A, and we would like to reject the word if it was accepted by automaton A. Okay, so let's give the formal definition of the automaton for the complement. Let A recognize L, and A will be our automaton with QA sigma delta A QSA FA. We construct M, once again, 5 tuples that recognizes L complement. As the set of states will be the same, Q equals to QA. The sigma alphabet will be the same, sigma equals sigma A. Transition function delta will be the same, identical to delta A. Initial state QS will equals to QSA, but in finite state we have a change. We will have now here a set of all states Q such that Q was not an accepting state at the automaton A. Another definition, F equals QA minus FA. So basically, to verify that we built what we actually were supposed to build, we have to prove that if W belongs to LA, it happens if and only if W does not belong to LM. The next operation is set minus operation. The class of regular languages is closed under minus operation. That means if we have L1 regular language and L2 regular language, then L1 minus L2 is also a regular language. To prove this fact, we can build an automaton, or we can use the stuff that we learned before in the set theory. L1 minus L2 can be defined as L1 intersection L2 complement. Since we showed that the family of regular languages is closed under the complement, we know that L2 complement is a regular language. Since we showed that the family of regular languages is closed under intersection operation, we have L1 intersection N2 complement as a regular language. Therefore, we actually proved that L1 minus L2 is a regular language. Okay, our next and last operation for this lecture is concatenation. Concatenation of L1 and L2 is also a regular language. The definition of concatenation, L1 concatenation L2, we have a set of all words with prefix x that belongs to L1 and with suffix y that belongs to L2. So if we have L1 language with two words A and B, and L2 the language with two words 0 and 1, 1, then we know that we have the resulting language for the concatenation operation is A0, A11, B0, B11. So the theorem is, if L1 and L2 are regular languages, so is L1 concatenation L2. Or the family of regular languages is closed or are closed under concatenation. Okay, let's think about how do we build an automaton for concatenation operation. If we will take once again L1, the language that accepts all words ending with 0, and L2, the language of all words having odd lengths, then basically we will start running automaton, a new automaton on language L1. We will define or we will identify that we finish reading some prefix, and then we will continue to run or we will move to the automaton B of the language L2. The only problem, giving a string W 0, 1, 0, 0, 1, 0, the idea, how do we know which part is the prefix and which part is the suffix? Do I stop after reading the first 0? Do I read 0, 1, 0 as a prefix? Do I read 0, 1, 0, 0 as a prefix? How do I know? Where do I finish reading prefix and where do I start reading suffix? So basically, we need some kind of lucky guess to know where to stop reading the first half of the word and when to move to the second half of the word. The basic idea behind concatenation that we need to construct an automaton M that will break the word W into two parts, a prefix U and the suffix V, and we will check that the prefix U belongs to L1 and the suffix U belongs to L2. But we have a problem. We can have several possibilities for the prefix and several possibilities for the suffix. So to solve this problem, we need some kind of new approach, and this new approach will be non-determinism. In order to prove that this family of regular languages is closed under concatenation operation, we will use a new concept called non-determinism. So basically, we will have some kind of help, let's call it an oracle, that a non-deterministic machine will be lucky and will have a lucky guess and will decide where do we have prefix and where do we have suffix. So basically in non-deterministic finite automaton, we can have transition like we have here. I can move from Q1 to Q2 with epsilon transition without reading any letters. I can decide to switch from Q1 to Q2. Sometimes from Q1 and input like 1, I will have two transitions like here. From Q1, I can move on 1 to Q2 and Q3. And sometimes I will have not defined transition. For example, here I have Q1 And please pay attention. For 0, I don't have any definition what to do. So I have an empty set. I don't know what to do. I don't know where to move. Okay, let's see an example. We are giving a non-deterministic finite automaton. This automaton has 4 states, Q1, Q2, Q3, Q4. Q4 is an accepting state. How do we know that this automaton is non-deterministic? Please pay attention. For example, in Q1 and 1, I have 2 possibilities. Staying in Q1 and moving to Q2. From Q2 to Q3, I have a transition with epsilon, so I can move without reading any input letters. And for example, in state Q3 and 0, we have undefined transition, so we don't know where to move. So let's see what happens with our non-deterministic finite automaton on the word 0101. So basically, we move to the first state, Q1, and on the input 0, we have only one possibility to stay in Q1. On input 1, now we have several possibilities. The first one, staying in Q1. The second one, moving to Q2. And the third one, after moving with 1, to use epsilon transition and to move from Q2 to Q3. Okay, now we have the next input letter 0. In Q1 with 0, we stay in Q1. In Q2 with 0, we move. In Q3 with 0, we don't have. In Q3 and 0, we don't have any transition, so we can't continue. In Q2 with 0, we move to the state Q3. Now we have the last letter, 1. In the first state, Q1, we can stay in Q1. We can move into Q2. And we can continue moving with epsilon. And we can reach also Q3. And from Q3 with 1, we move to the Q4, which is an accepting state. So we have now 4 possible choices. We can finish reading our word in the state Q1. We can finish reading our word in the state Q2. And we can finish reading our word in the state Q3. And also Q4, which is an accepting state. Since one of the possibilities is an accepting possibility, we decide that the word belongs to the automaton, to the language of the automaton. So basically, we need only one transition, only one path ending with an accepting state. All the rest of the paths can be not defined like we had, or can finished with a rejecting state. So let's compare deterministic computation and non-deterministic computation. In deterministic computation, for each state and for each input letter, we have one unique transition. So basically, we are talking about one path. We started from the beginning initial state. We move each letter of the alphabet to the next state. If we finish reading the word in the accepting state, we accept the word. If we finish reading the word in the rejecting state, we reject the state. With non-deterministic computation, we can have several possibilities for each state. So basically, we have a state and an input letter, and we have several choices. So we have to build several paths, or we have to build a decision tree where we have several choices. And we continue like this. Some choices can be cancelled during our computation, since, for example, we didn't have a definition what to do at the state Q3 on 0. And some computation will be finished till the last letter, and the result will be that we have to reject the word. But if we have at least one computation ending with an accepting state, then we know that the word belongs to the automaton. So from our point of view, when we have a decision tree of all the paths, it's enough for us to find one path ending with an accepting state. So if we will take our non-deterministic previous automaton as an example, and let's say that we have a word 0110, we we claim that the word 0110 belongs or accepted by the language of the automaton because there exists a path that starts in an initial state Q1 and leads us to an accepting state. Let's see the path. Q1 on 0, we can stay in Q1. Q1 on 1, we can move to Q2. Q2, we can jump with epsilon transition to Q3. Q3 on 1, we can continue to Q4. Q4 on 0, we stay at Q4, which is an accepting state. Therefore, the word W is accepted by automaton. When do we claim that the word W does not belong to the language of the automaton? After checking all the possible paths. If we know that all the paths are actually ending in rejecting state, we claim that the word does not belong to the language of the automaton. And in this case, we reject this word. Let's see an example. Let's take a word 1 as an example. Let's run our automaton. For 1, we have several possibilities. We can start reading 1 in Q1 and we can stay in Q1, which is non-accepting state. We can move with 1 from Q1 to Q2, which is not accepting state. We can use epsilon transition and move with Q1 to Q2 and use epsilon to move to Q3. But once again, we finished reading the word in non-accepting, in rejecting state. Since all the paths that we checked end with rejecting state, we know that the word 1 does not belong to the language of our automaton. So if we need to compare between non-determinism and parallelism, we can claim that for any string W, the non-deterministic automaton actually is a set of possible states, the set of possible paths, the set of possible results. If the final state of possible states or possible paths contains an accepting state, then we know that the automaton accepts the string. If we check all the paths in parallel fashion and we don't have an accepting state, then we reject the word. So basically, instead of moving in from one state to another state to another state, we now continue to move in parallel, and that is why we have a tree and not a single path. So in non-deterministic automaton, we have several paths as a result, or we can have several paths as a result. So let's give a formal definition to non-deterministic finite automaton, abbreviation NFA. A non-deterministic finite automaton, NFA, A, is defined by a 5-tuple, Q, sigma, delta, QSF. Q, we have a finite set of states, not empty. Sigma, we have finite alphabet, usually not empty. Delta, we have a transition function. Please pay attention. Delta is now defined for Q Cartesian product sigma with a small index of epsilon, since we have also epsilon as a legal input, and the result is a power set of Q. The result can be several states, so we are talking about set of states. So basically, delta Qi sigma equals to some set Qj, Qk, whatever. Qs will be some initial starting state. F will be a partial set of Q, and F is actually a set of accepting states. So new thing from our point of view is actually transition function. Now the function delta for each state and each input letter, including epsilon, we have several possibilities. So we are talking about power set of Q. That means that delta QA equals R, where R can be a partial set of Q. Additional change that we have here, we are talking about alphabet sigma with index epsilon. So epsilon is actually edited to our alphabet. So the new alphabet is sigma, previous alphabet, union with epsilon. Please pay attention. Sometimes our transitions can be not defined. So delta for Q and A can be not defined. That means that we have an empty set as a result. So let's give a formal definition for the automaton that we previously had. Set of states Q. We have 4 states, Q1, Q2, Q3, Q4. Our alphabet is 0, 1. Transition function is written in this table. Please pay attention that we have all the states as rows, Q1, Q2, Q3, Q4. We have all the letters of the alphabet, 0 and 1, as the columns, but also we have additional column, which is epsilon transition. For Q1 and 0 in this automaton, we have a result, a set with Q1. For Q1 and 1, we have a result, a set where we have Q1 and Q2. We still don't add Q3 because to move to Q3, we also have to use epsilon. Q1 on epsilon, the transition is not defined. Let's see Q2. Q2, when we have input 0, we move to the set with Q3. Q2 on 1 is not defined, so we have phi, an empty state set. Q2 on epsilon also moves to the set with Q3, and we continue the same way. The initial state in this automaton is Q1, the state where we have arrow entering it, and the resulting final state in this automaton is Q4, since it's the only state that is an accepting state. As usually, after defining the automaton, we should define what is the language of this automaton. The language of an NFA A is a set of words that A accepts or recognizes. That means that we read the words and we might stop in an accepting state. So we have all the words that after checking all the passes, at least one pass was an accepting pass. If we need to define the language of NFA in a formal way, we are talking about L of the automaton A that equals to all the words W such that W belongs to sigma Kohavit, to sigma star, and delta cap QSW intersection with F, a set of finite states, is not a zero state, which means there exists a path from QS to some finite state R when we start reading an input W from the state QS, we finish reading it at R and an accepting state. Please pay attention. Then once again, delta cap QSW, we have several possibilities. We have a set. So we are talking about intersection with F, and if this intersection is not empty, then we accept the word W. Language of NFA, even more formal definition. When we have some non-deterministic finite automaton A, we tell that A accepts W if we can rewrite W as a set of letters B1, B2 till Bm, with each Bi belonging to sigma epsilon. And now we have a sequence of states R0, R1 till Rm, such that R0 is a starting state, R0 equals QS. Each transition is defined by automaton. Delta Ri on the letter Bi plus 1 is actually leads us to some state r I plus hat, which is r plus I plus 1, which is a state of the automaton, and Rm, the final state that we finish reading the word, belongs to F, the set of final states of the automaton A. Okay, let's practice. Let's build some non-deterministic finite automatons over alphabet 0, 1. Actually, it's a question from Sipser book 1.5. We have here 5 languages. 2 of the languages we will do today during the lecture. 3 languages we will have for our practice exercise that we will have during our next Zoom meeting. So the first language is the language of all words W, such that the penultimate letter in W is 0. The letter before last is 0. And you have here some hint. You have to build it with 3 states. The next language is only language that accepts 0, and we will build it with 2 states. The next languages, 3, 4, and 5, we will do during our practice exercises. So I want to build an NFA, non-deterministic finite automaton, for the language L that accepts all the words with penultimate letter W is 0. So I would like you to store the lecture recording and to try to solve this problem by yourselves. I will continue with the solution. Okay, basically I will need 3 states. The first state, I will move from Q0, the starting state, to Q1 with 0, and this will be the letter before last. From Q1, I will move to Q2 on 0 or 1. I need additional letter. It can be 0 or 1. In Q2, I don't define what I would like to do because 0 or 1 that I had should be the last letter. In Q0, for all the prefixes before the 2 last letters, I am staying at the self loop. So in Q0, I stay for 0 and 1 in Q0. I claim that the automaton that I built actually accepts the language of all words penultimating with a letter in W is 0, or having the letter before last 0. Okay, let's move to the second language. Once again, we were asked to build a non-deterministic finite automaton. Actually, we did this question at the beginning of the lecture, but we had to build a deterministic finite automaton which accepts only one letter A. So now we are allowed to build non-deterministic finite automaton, and you were given a hint, 2 states will be enough. So please stop the lecture and try to solve this problem by yourself. I will continue, and here we have the resulting automaton. We need to move from Q0 with 0 to Q1, which will be an accepting state. That's it. All the rest I don't want to accept. I don't want to have any prefixes. I don't want to have any suffixes after Q1. So I definitely define only what I needed. All the rest is missed from my automaton. Please pay attention. The next three questions we will do during our practice exercise. We will build a non-deterministic finite automaton for the language L that accepts all strings W that contain even number of zeros or exactly 2 ones. Then we will do the same, but we are talking about all words W or about all words W that contain even number of zeros and, not or, and exactly 2 ones. And the last one, we would like to build non-deterministic finite automaton that accepts the language of zeros. So we have 0 in power of n, where n is a natural number. Additional questions for our practice will be to describe an NFA for the language that is 0 in power of I, 1 in power of j, where I modulo 3 equals 1 and j modulo 2 equals 1. We will have to build an NFA. The next question will be give a formal description of this NFA. So we will build a 5-tuple, or we will define the 5-tuple. The next question will be what is the language of this NFA? Once again, we are giving a drawing and we have to define the language of this non-deterministic finite automaton. And our last task for practice meeting will be to build 3 types of automaton: deterministic finite automaton, non-deterministic finite automaton with no epsilon transitions, and non-deterministic finite automaton with epsilon transitions from the language LW such that W belongs to 1 star, 2 star, 3 star. So we have prefixes of 1, then in the middle we have substring of 2s, and in suffixes we have only 3s. I would like to thank you for listening. This is the end for our part 1 meeting on Unit 3. Unit 3, we are talking about non-deterministic finite automaton, and we talked about closure of regular languages or regular operations. We will meet during our Zoom meeting and solve several problems together. Next week, during our next meeting, we will continue to talk about non-deterministic finite automaton.